Let's talk now about the origin of the infrared bands, that is spectroscopy, and what are we learning then. In the previous video, we talked about the UV visible, and what we're looking in the UV visible when we have conjugated systems such as this, we're looking at electronic transitions. And in the case of this butadiene, where we have, say, these are my 4 molecular orbitals. These are the bonding NMOs, and these are the anti-bonding up here. For butadiene, we have 2 of the orbitals, the 2 lowest in energy, occupied. This is my HOMO, highest occupied molecular orbital, and the next one is the LUMO, so lowest in energy, unoccupied molecular orbital. And what UV visible does, we have some light at some particularly specific wavelength so that it excites that one electron to jump up, and that's associated with an absorption band. So we call that, we get this information, lambda max. But bottom line, what we have is an electronic transition. Now, when we are in IR, we have light that is of less energy. So when you have in the spectrum, for example, this is the visible range from 100 to 700 nanometers, 400, 700 nanometers. But below that, we have the infrared. And what it is like longer wavelengths. This is IR. And the longer the wavelength, the less energy you have. So this is your Planck equation. Let's remember that. Or you can also say hc over lambda. So going to this side is less energy, so longer wavelength. Here you have infrared, and then you have the microwave, for example, region of the spectrum. So these are my regions. I should have done it differently, but anyways, it looks crowded. So visible here. UV is here. And now I have on the right-hand side, I'm going to have IR. And here, I'm going to have microwave, for example. And here, this is the UV visible, where we have the electronic transitions. Now, what are we observing in IR? Well, in IR, what we observing is smaller energy levels that are being excited. And these are vibrational levels. So we can think of the ones, we use the harmonic oscillator model. So meaning springs here, the 2 masses joined by a spring. So this is the harmonic oscillation model. What I have here is water. This will be ammonia, and this is methane. So all those bonds are flexible. So we see this vibrates. And not only that, they vibrate in different ways. For example, you can have stretching, and you can have bending or scissoring. There's a number of vibrational modes. That's why we call them. Here you can have this moving this way, or rotating even. A lot of those. Those are tiny energy levels. So in looking at the gaps, it's like I have, say, 1 electronic level. That's my harmonic oscillator. In the other electronic level is here for my HOMO-LUMO transition. But in between, I have these tiny levels. These little things are vibrational modes, or vibrational levels of energy. And this is what I have. So energy is going up here. Let's say this was my HOMO, and this was my LUMO. So when you do UV visible, you're jumping from here to here, and that takes more energy. And now when you do IR, you're just using this tiny gaps. And because this is smaller, these gaps, now we need less energy, and that is longer wavelengths. So longer wavelengths are to the side. So when I have in the electromagnetic spectrum from the visible here, you're increasing here. In this direction is increasing wavelength, and therefore decreasing in this direction energy because of that relationship. So that is the origin, and we will be then analyzing a spectrum using this. So, but the idea in general is electronic transitions for the UV visible vibrational transitions that we're going to be seeing, and there are several modes, as we said here in with our models. I like those models to have the springs. This is my lone pair in ammonia, my thing. So bonds are not statics, and there will be those vibrations, and this is the origin of the bands that we have in the IR.